Hi guys, in this video we're going to look at integral calculus and how it was generally the process of understanding how it works, how we use it in GCSE and the ways you'll need to know it, and just generally get a sense of what it is. So we've learned about differentiation in the other unit and all its applications, and now it's time to focus on integral calculus. So the GCSE exam board doesn't go as deep into integral calculus as it does into differentiation, probably because integral calculus is slightly more tricky and it's not really got as many uses, like separate distinct uses as differential calculus, but it's still very, very important. So I've just drawn a graph here and I'm going to explain how we can relate this to integral calculus. So let's start off by letting this graph equal f of x. So we recognize that as a function. Now, what we want to do is try and find the area underneath the curve f of x. So I'm just going to draw a line here because this is where we're going to let the curve end. Well, let's say we want to find it in between these regions. It's over here. And in order to find the area, well, it's a curve, right? So we're going to try and break it down into parts where we can actually evaluate it. So we're going to break it down into rectangles because those are things that are very easy to calculate in terms of area. So this here is going to be a rectangle. Then we have another rectangle, ignore the messy drawing, another rectangle, and so on and so forth. And as you can see, this rectangular approach isn't that useful just because it's leaving big gaps with these triangles over here. These triangles are part of the area, but they're not being accounted for. So what we have to do is we have to find a way to make these rectangles as perfect as possible to the point where there's no wasted area. So let's try and make the rectangles even thinner so we're able to maximize that. So thinner means we're gonna, let's say, go to here first. That's a very thin rectangle. Let's keep going. Another thin rectangle, another thin rectangle, etc. And we keep going on. And as we can see, the thinner and thinner it gets, the smaller and smaller these triangular gaps get. And the less and less wasted space we have. So integration uses that principle. It's not so much that we're using distinct rectangles so much as we are using the idea of the rectangle. So integration is the principle that as we make the width so small that's practically zero, then we can sum all these rectangles. So let me just draw one rectangle. So let's say this rectangle over here, let me draw it again. Let's say that this rectangle over here had a width of, well, 0, or we can represent it as dx. So dx would mean delta x, which is basically the change in x. So basically, the change in x in terms of the width is represented by integration. And we have many more rectangles. I could start filling them out again, but for the sake of time, we're not going to. So we have many rectangles with a width of dx. We're not going to make it 0 because they do have a width technically, but it's not in terms of rectangles, if you're understanding what I'm saying. Then the height of this rectangle is equal to f of x, right? Because we're just we're just connecting the line to the graph directly across. We're not going up or down with it. So it's just a straight line to the graph. So this height will be f of x. So now what we can say is the area of this rectangle is f of x times dx. And what we want to do is sum all the rectangles. So if we can use our sigma sign as the sum, we get f of x dx. Now, we're not done here because the width is technically dx, which we can see is very, very, very close to 0. It's just a slight change in x. That means that technically there can be infinite rectangles. So this sigma sign, we're going to replace with an integral sign, which represents that we're using those infinite rectangles. And there we are. That's kind of how we find the integral of a function. That's what we denote an integral to be. And that's how we view it as the area under the curve. So we can actually calculate many areas under the curve using this f of x dx notation. And you'll see that there will be the dx in many examples. Well, I might forget a dx, or I meant to put a dx. The dx is important because it represents that width that can't be quantified with a constant. Alright, so now we've gotten how the rectangular approach and delta x, or dx, allows us to construct the integral of f of x of dx, which is that key fundamental part of integral calculus. Let's go into the applications that GCSE requires us to know. So area under the curve is the first one I mentioned. So we can do this with both indefinite and definite integrals. So indefinite integrals are basically integrals that are not defined by bounds. So when we have the integral sign, and f of x dx, the bounds go in here in a and b respectively. In indefinite integrals, those bounds don't exist. So you're just finding the general solution without the bounds. So, for example, if f of x is 1, then the integral of f of x dx is x. So that's general solution without substituting any bounds. Definite integrals substitute those bounds in. So this will make more sense later, but when we put in b and a, this would come out to b minus a instead, which is a specific solution to those bounds. So typically when you're finding the area under the curve, you use definite integrals because you're getting a constant using the bounds, because technically the area under a curve could be infinite. However, if we're finding it between two bounds, like let's say these two bounds, these two bounds I've identified over here, these red lines I'm drawing over here, in between here, the area over here is a constant. It's not infinite. It's finite. That's why it's called definite integrals, because you can get a definite answer to it. Then the second application, area under the curve, the extension of that is you can also find it between curves, between the curve and the y-axis, etc. There are more applications that we don't cover at GCSE, such as volumes of revolution, but you'll come across in IB HR Maths, for example, or in another course. Then the second application of integration that we cover here is kinematics. So kinematics we actually cover in differential calculus as well, but this is one of the unique areas where both integral calculus and differential calculus prove vital. So kinematics involves going from displacement to velocity to acceleration, things to do with particles and physics. You will be using a lot of integral calculus to help you with that. But more on that will be on the other videos where I actually go deeper into those concepts. So hopefully this provided you with an understanding of how integral calculus works, and thank you for listening, and see you in the next one. Goodbye.